We have seen how to draw shear force and bending moment diagrams for beams in the previous lecture. Now in this lecture we will see how to use the shear force and bending moment values to get the stress in beams. To elaborate, I take the example of cantilever beam again. Cantilever beam has a length of L and it is loaded with a point force at the end of P. Obviously, it can be easily deduced that this beam will bend like that under the application of the force. So, to quantify the bending, which is to figure out how much stress is occurring, we have to make a few assumptions. The first one of them is that the length is far more than the width and the thickness of the beam. That is the first assumption, and it's important. What that tells is that the only dimension of the beam which is going to be affected significantly by the bending moment is the length. The second assumption is that the cross section shear strain is insignificant. Compared to the bending stress. The third assumption is that there is something called a neutral axis in the beam which doesn't have any stress or strain. Normally it lies at the center of the beam. And the fourth assumption is that the cross section remains normal to neutral axis before and after bending. So if we have these four assumptions, we can arrive at the formula of bending, which is m upon I is equal to sigma upon y is equal to E upon R, where m is the bending moment, I is the second moment of inertia of the cross section, sigma is the stress at a particular location along the thickness of the beam. So let's say this the location is here, so the sigma is defined there. Y is the location of that particular y is the distance of that particular location where we are figuring out the stress from the neutral axis. E is the Young's modulus and R is the radius of curvature of the beam. So this R will be like this. At this point, this is the radius of curvature. Now the formula is by itself seems to be like very easy, but let's see how to apply this formula in practical problems. So let's take the first case, which is here itself, which is the bending of beam. So we have to find out what is the maximum stress because of bending. So for that, first we have to figure out what is the maximum bending moment. So the bending moment maximum value for this beam, this cantilever beam, is PL. Feed in the value here and we get sigma is equal to m upon I multiplied by y. So if I just draw the cross section, this is the cross section of the beam and this is y direction. So y max is t upon 2 because this total length is t. So sigma max occurs at y max. So it will become m, which is PL into t upon 2. Now what is the value of I for the rectangular cross section where this dimension is b? It is 1 upon 12 b t cube. So that leaves me with the value of sigma max as 6 PL upon b t square. That is the maximum bending stress in a cantilever beam, and this bending stress occurs at this point and at this point. Now because the bending is happening like this location is compressed while this is under tension. So here bending stress is minus 6 PL upon BT square, while here it is plus 6 PL upon BT square. That's a simple case to start with, but the case may not be this simple. Let's see another case, which is that of a simply supported beam. So we take a simply supported beam. Again, the length is L and the cross section is BT, and there is a force P acting at the center of the beam, where this is L by 2 and this is also L by 2. Now here in this case, the maximum bending moment is PL by 4. This we know from the previous class. So in case of this, the maximum bending stress will be given by PL upon 4 into T by 2 into 1 upon 1 by 12 PT cube. I just modify this equation. I get 3 by 2 PL upon BT square. That's the maximum bending stress in the simply supported beam with a load P at the center. So these two are very simple cases. This is a simple case of cantilever and this is a case of simply supported. In reality, the problems will be more complex. So let's see how to create a slightly more complex problem than this. So I take the cantilever beam again and I apply force P at the free end, which is inclined with the horizontal axis by an angle of theta. So obviously I have to resolve this force into two parts. This is P sine theta and this is P cos theta. Now, P sine theta causes the bending, and because of which the maximum bending stress will be same thing as what we have got here, which is 6P. Now P becomes P sine theta L by Vt square. This is not the maximum stress in the beam. This is only the maximum bending stress. So this maximum bending stress occurs here and here. Here it is tensile, here it is compressive, this is compressive, this is tensile. Now along with this there is a tensile force of P cos theta. So there is a tensile stress sigma max tensile, which is equal to P cos theta divided by Bt. And this is a uniform stress everywhere in the beam. So the total stress is equal to 6P sine theta L upon Bt square plus P cos theta upon Bt. I can take P upon Bt as common. So that leaves me with 6L by T sine theta plus cos theta. Obviously it's easy to see that if theta is equal to 0, which means that the load is totally horizontal, then there will be only uniform tensile stress of P upon Bt. If theta is 90 degree, which is only a point load which is transverse, then it will be PL upon Bt square into 6, or rather 6 PL upon Bt square, which is nothing but the bending stress for cantilever beam. So this is a slightly more complex problem. Now let's see one problem which is much more complex than this, and that's the case of combined loading. We have a cantilever beam, a simply supported beam, which is like this. There is another piece of material added to the center of the beam. This is the center of the beam. This is L upon 2 and this is L upon 2, and the length of that extra material is A, and there is a force, horizontal force of P acting there. Now for this case we have to figure out what is the maximum stress in the beam, not the maximum bending stress, but what is the maximum stress in the beam. Let's see how to solve this problem. So the first thing is that if we isolate the beam alone, the beam can be isolated like this. There is a longitudinal force P and there is a moment counterclockwise of PA, and this is, let's say, RA and this is RB. So obviously we know for this case the maximum bending moment is given by PA by 2. So the maximum bending stress will be PA by 2 multiplied by 1 upon 12 BT cube multiplied by T by 2. So that gives me 3 PA upon BT square. That's the maximum bending stress. Now this maximum bending stress is occurring at this point. Is it right? No. This maximum bending stress is acting at this point actually. Sorry. This point there is no bending moment. It's the maximum bending stress at this point. So at this point, if I again take the case, so I have the beam which bends like that. At this point, sigma max B is equal to 3 PA upon BT square. Right. Now besides this, there is a longitudinal stress which is again uniform because P is uniform. So that will be P upon BT. So the total stress, sigma total, is 3 PA upon BT square plus P upon BT. So if I just take P upon BT as common, it becomes 3A by T plus 1. So this is the maximum stress which is occurring in the beam, and that point is the point at the central cross section where the extra projection is added, and at the bottom of the beam there. So this is the maximum stress in the beam. Now obviously we can make problems more complex, but the phenomenon doesn't change. It may be a case of multiple loadings, but for each loading we can figure out the stress because of bending and because of the longitudinal force and add them up algebraically to figure out what is the maximum normal stress in the beam. Now besides the bending moment, there is a shear force in the beam also, and obviously there will be some kind of effect because of the shear force also, and the effect of the shear force is to induce a shear stress in the beam. So let's see a simple case wherein there is a beam which is bending like this, and let's say that we are seeing this particular location of the beam. So it's let's say this length is some small ds, its height is t, and its width is b. So it has been found that the shear force, or rather the shear stress, is given by the shear force multiplied by the first moment of inertia of the area of cross section divided by its second moment of inertia of its cross section, and B. B is the width of the beam. Now, obviously, for rectangular beams, for example, which are the most common, if I draw the cross section, rectangular beams are like this, and this is the central line, which is nothing but the representation of neutral axis, and its width is B and its thickness is T. So for this beam, we can take the upper half, and for the upper half, Q is equal to the area of that upper half, which is B upon 2 multiplied by T, multiplied by the distance between the neutral axis and the center of gravity of that area, which is nothing but T by 2. T by 4. So that will become Bt square by 8. Now if I feed this number into the formula, I get tau as V upon I multiplied by Bt square by 8 into B. Now I is nothing but 1 upon 12 Bt cube multiplied by Bt square by 8B. So I simplify this formula, it becomes 3 by 2 V upon Bt. Now let's see what is V upon Bt. So if I have the shear force which is like this, V upon Bt is a sort of average shear stress in the cross section. So the maximum shear stress is 3 by 2 times average shear stress in the rectangular cross section. Now for rectangular cross section, now if we write the same thing for circular cross section, it becomes 4 upon 3 into tau average. This is for circular cross section. The variation of shear stress is also a very important phenomenon, and let's see how the shear stress varies over the cross section. Now I take the example of cantilever beam again to elaborate. So I have this cantilever beam and its length is L. There is a P acting here, which is the shear force on the beam, and the cross section of the beam is rectangular. So the cross section is like this. There is this thickness of the beam, which is T. There is this width of the beam, which is B, and the shear force P is applied like this, P. So here we can see that if I ask you what is the shear stress in the beam, you will say, okay, P upon Bt, because shear force by definition means the shear stress by definition means the shear force divided by the area of cross section. But this is not correct. This is the average shear stress in the beam, P upon Bt. But let's see what is happening to the beam. See, the bottom face of the beam is like this. So this is the bottom face of the beam, and this is the top face of the beam. Both these faces, the bottom face and the top face, do not have any applied shear force. Hence, there the shear stress cannot be there. But seeing the formula, it seems that there is a shear stress there. That's not correct. So what happens is that the shear stress is actually 0 at this point and at this point. So if I just take the beam again and draw it in 3-dimensional view, so at this point tau is equal to 0, and at this point tau is equal to 0, and at the center it is maximum, tau max. and the variation is a parabolic variation like that, where this value is tau max, and this is 0 and this is also 0. So the shear stress in the cross section of the beam varies like a parabola, and its maximum value, for example, for rectangular cross section is 3/2 times its average value. Now let's see a couple of problems about the shear stress. Now for a simply supported case, which is like this, I have a force P acting anywhere on the beam, doesn't matter, and the width is B and the thickness is T. So the shear stress average value will be P upon BT. But the max shear stress value tau max will be equal to 3/2 of P by BT. The reason is that the shear force anywhere in this beam is P. So these are the average and maximum values of shear stress in this beam anywhere in the beam, and they occur at the neutral axis. Now let's go back to the problem which we had seen previously, which is that there is a simply supported beam with a projection here and there is a force P. Now in this case, we know that the maximum shear stress, maximum shear force is nothing but equal to the reaction, and the reaction at any location is if this length is A, this moment is PA, so the reaction is PA by L. So the shear stress in this, shear force in this case is PA by L, and this is minus PA by L. So in this case, the average shear stress will be equal to PA by L into BT, while the maximum shear stress will be equal to 3/2 PA by LBT. Now you see, LBT is the volume of the beam. Now let's get back to the problem of what is known as traction. So in this case, for example, I can say that the traction, which is defined as the square root of the sum of squares of the normal and shear stress at a particular location. Now if I ask the question as to where is the traction highest, now obviously the answer will be dependent on whether the value of sigma at the bottom point is higher or whether the shear stress value at the midpoint is higher. So the reason is that traction, let's say I take this point as C and the center point here as D. Traction at C will be defined as sigma square root of sigma square only, which is equal to sigma, because there is no shear stress, and this value we have seen from the previous example is equal to 3A upon T plus 1 into P upon BT. Right. Now traction at D, and D is the point here, this is point D. If I just zoom the beam, so the beam is like this, and this is the projection attached here. This is point D and this is point C. So traction at point D is sigma square plus tau square. Now there is a sigma because there is a direct or there is a longitudinal stress which is P upon Bt. So if I just square root that, square it up, plus the value of tau there is, the maximum value of tau is this much, 3 by 2 Pa upon L Bt square. I can take out P upon Bt common, 1 plus, this should be inside, 9 by 4 Pa by L. Now obviously out of this and this, whichever is higher will be dependent on whether this value is higher than this value. So this is how we figure out what is the maximum traction in the component. And one thing to note here is that the traction is the number which is used to design the beam or to design any component. So this is how we figure out the stresses in beams, and this is one of the most important considerations in designing beams. So I request you to please pay a lot of attention to how to get the shear stress and the bending moment diagrams, and how to use those values to get the values of the bending stress and shear stress in the beams, and how to finally get a traction in the beam at various locations.